So in this last video, I want to talk a little bit more about reductions. Now we understand the basic idea of transforming a problem input so that we can use it for some other algorithm to solve a different problem and take that output and transform it back to solve our original problem. Then we understand that idea. I want to talk about a few more examples of reductions in practice. Firstly, one is to show you that reductions don't necessarily have to do with graphs. So I want to first start by showing you an example of a reduction that doesn't use a graph at all. And then I want to show you a really cool application that does use graphs kind of behind the scenes. So let's start with this problem of checking for duplicates. So I have an array of numbers. I want to compare all of the numbers in the array to make sure that there aren't any duplicates. No number is repeated. Now you could probably pretty easily come up with an algorithm for this that kind of does this nested loop over all of the array elements and checking each pair of elements and making sure that there are no duplicates and returning true and false appropriately. And using the tools that we talked about early in the quarter, you could probably kind of analyze this code and say, in the worst case, this would take something like n squared time. Because in the worst case, you're going to have to compare every single pair of numbers, which there are n squared of. And so our question here is, can we do better? This is one of the things that's important to think about as a computer scientist, is thinking about, are there better ways of approaching a problem? And there's not always a clear answer. Like, it's not obvious that there may or may not be a better answer than n squared. Now, one tool that we can help us to think through different solutions to a problem is to try to tackle this with a reduction. Can I reduce the problem of containing duplicates to another problem I have an algorithm for? So can I do a transformation here that transforms this problem into an input that's usable by another algorithm for a different problem, and then take the output of that algorithm and turn it back to the output of our original problem? Now, one of the things that's tough is each problem and its reduction is entirely specific to that problem. There are sometimes not very general tips for how to go about it. So it might not be clear when I suggest right now how I'm going to reduce this problem to another problem. That's okay if that suggestion of what's the problem queue that I want to use, if that's not clear, that's okay. The important thing is understanding how you can reduce something from one problem to another. Because deciding what problem you want to reduce to is a very hard problem. It's generally kind of a puzzle, thinking about what might be useful. You get that with experience. But the important part here is the mechanics of this. So what I'm going to argue to you is that this problem of contains duplicates reduces to sorting a list of numbers. So here's my proposal for how to do a reduction. Simply pass the array from the contains duplicate to some problem for sorting an array. Now in this course, we haven't talked about algorithms to sort an array. We'll talk more about that in a future week, but just know there are many such algorithms that take an array of numbers and put them in sorted order. Particularly, we'll talk about heap sort, merge sort, and quick sort. Okay, again, if those words don't make sense, we'll talk about them later. But those are specific algorithms to solve the sorting problem, taking an array of numbers and sorting them. So we could just take our array for contains duplicate, pass it to the sorting algorithm that will sort it, and it will output to us a sorted array. Remember, a reduction always has 3 steps. Transform the input, run this other algorithm, transform the output of that algorithm. For the transforming the input, we don't really have to do anything because the input for sorting is just an array of numbers and it will sort it. We get as output a sorted array, and what we'll need to do here is kind of go through that array to check for duplicates. But now on this sorted array, this problem is easier because we just check pairs of numbers. We iterate through the array. We look at every adjacent number. If we find a duplicate, we return false. Otherwise, we return true. This is going to be an O of n operation. Now, I like this example for 2 main reasons. One is it shows you that you could do reductions on things other than graphs. And 2, it shows you that the step of transforming your input or transforming the output don't necessarily need to be simple. For example, this third step of scanning through the sorted array for duplicates, that requires looping, it requires work, but that's okay for a reduction. The reduction just requires changing inputs and outputs. It requires that you don't change the algorithm that you're going to run. And so this is totally fine that we have to do extra work. Now, one thing we haven't talked about yet, because we haven't talked about the details of sorting algorithms, is the runtime of actually doing one of these sorts that we described here is going to end up being this n log n runtime. It's worse than O of n, but better than O of n squared. It's kind of in between. That is the time to actually takes to sort, which we'll understand why it's n log n later when we talk about sorting. But that's, I'll just tell you, is the runtime. It's n log n. But we also have this n term for this third step of searching through this the array for duplicates. But n log n will end up dominating n. So the runtime here is just n log n. And so this reduction here helped us avoid that quadratic runtime. We now have this n log n from sorting. We don't need this n squared. So reductions can be a really powerful tool in speeding up your algorithms. If you don't quite know how to solve a problem, or you have a kind of slow implementation, the key idea here in a reduction is, can you change perspectives? Can you change the problem somehow so that you can use an efficient algorithm for a different problem to help you solve it? And it's totally okay if the step of the reduction takes a little bit of work. As long as it's faster than the solution to your original problem, that's an improvement, which is great. Now, what I want to talk about for the last part of this video is a slightly different application of reductions that's very less clear than before. I don't even think the sorting application for contains duplicates was super clear. This one's even less clear, but I think it's cool to show you that there are really cool applications of this reduction. So the problem at hand here is what we're going to call content-aware image resizing. So suppose I have this image on the left, picture of a person and a castle, and I want to scale the image so that it's less wide. So one way of doing this is to actually kind of just try to shrink the image horizontally, but that's going to cause all of the objects in the image to be less wide. They don't preserve the kind of original dimensions. And so the algorithm that we're going to introduce here is this one called the seam carving algorithm. The idea is it's trying to remove irrelevant parts of the image and preserve the sizes of the important parts of the image. So for example, here is a seam carved version of the original photo that kind of removes all of the background sky that's not relevant, but while preserving the castle and the person. So before I describe the algorithm, let's talk a little bit about, and the reduction to do that, let's talk a little bit about kind of what this looks like. And to do that, I'm going to have a presenter from YouTube. A presenter from YouTube show this to us. So I have here a video from SIGGRAPH. SIGGRAPH is a conference on computer graphics. It's part of the special interest groups from the ACM. It's an organization that does computing conferences. This video is from 2007, so a little over 10 years ago, a little less than 15 years ago, where they introduce this idea of seam carving. So I'm going to go ahead and let them explain this for us.
Seam carving for content-aware image resizing. Digital media today has the ability to support dynamic page layouts. By changing the window or display size, we can change the layout of a document. However, images embedded in a document typically remain rigid in size and shape. Resizing is also important to fit images into different displays. Current techniques, including cropping or scaling, are limited in their abilities to capture the image content. We present a method for content-aware resizing of images. Our technique enables resizing while adapting the image content and layout. This is sometimes called retargeting. We also define a flexible multi-size representation for images that supports continuous resizing. An image can be shrunk in a non-uniform manner while preserving its features, but it can also be extended beyond its original size. Instead of scrolling through images that do not fit in a given display, we gracefully resize them to fit inside the window. For example, assume that we need to change the width of an image. The simplest way to do this is to remove columns of pixels from the image. The best column to remove would be the least noticeable or least important column. We can search for this column by defining an importance or energy function on the image. In this example, we use the gradient magnitude of the image. Next, we look for the column which contains the least energy and remove it. However, using such an approach quickly leads to serious artifacts. Therefore, instead of using rigid columns, we search for connected paths of pixels, or seams, from one side of the image to the other that contain the least energy. This can be done using a simple dynamic programming algorithm as described in the paper in both vertical and horizontal directions. Here's another example of an image, its energy function, and the least noticeable horizontal and vertical seams. By successively removing horizontal and vertical seams, the image can be resized in a non-uniform manner. The order of seam removal in an image defines an order on the pixels of the image. By storing the simple indexing information, we create content.
Okay, I'm going to go ahead and stop this video. There's a link in the slides if you want to finish the rest of it, which is pretty interesting. But the key idea there was we just talked about this idea of cutting down on pixels in an image, but instead of just removing a column, kind of smartly going about cutting it down a path. And the way they defined that path was this kind of path of least energy, which they describe as essentially thinking of the energy of pixels as being how different that pixel's color is from a neighboring pixel. So what we're going to do is it turns out that this problem is essentially able to reduce to Dijkstras. That we can just take this seam carving, identifying a seam in an image, and turning it into a problem that Dijkstras can solve. So a reduction always requires 3 steps. Requires transforming the image, taking the image and turning it into something that we can use for this other problem. Dijkstra's operates on graphs, so we need to turn this image into a graph. So here's the big idea for how to translate this image. So suppose we take this image of this absurdly cute dog, and we want to seam carve it, preserving the dog's face, obviously, with being able to remove the background. So what we're going to do is we're going to define, in order to define these paths of kind of least energy, the ones that have the smallest change in colors, which probably correspond to backgrounds, we want to be able to define a path that has a lower weight if it has smaller pixel differences. So the graph we're going to define is kind of a weird one. It's a reduction from an image to a graph that we can run Dijkstra's on. Each vertex is going to correspond to a single pixel in the image. So each kind of little square that shows the color of the picture is going to be a pixel or a vertex in our graph. And we're going to kind of weirdly define the edges as going downwards. So each pixel will have an edge to all of its downside neighbors, being the pixel below it, bottom left, and bottom right. And we're going to find the weights of these edges as being the energy, which is kind of the visual difference between two colors, those two colors. Then this problem just is essentially Dijkstra's. We run Dijkstra's to find the shortest path down this graph, right? The shortest path would be the one with the smallest edge weights, which would correspond to the one with the smallest energy, which should be the part of the image that has the least information, the least interesting parts. Then, once we've identified this path using Dijkstra's, we just have to transform this graph back to the original image to say, oh, what parts do we actually want to remove? This is the power of reductions. There can usually be totally non-obvious ways of transforming one problem to another that result in being able to solve a problem using a tool you already know. In that video, they talked about this thing called dynamic programming, which I think we'll have a little bit of time towards the end of the quarter to talk about. But you don't even need any of that if you're able to see a reduction, which in this case is not clear. Like, I don't expect you to be able to look at this picture and be like, oh, I obviously know where the reduction is. That's probably pretty tough. But if you're able to see the reduction, that's a really useful tool in helping solve one of these problems. Now, I will mention this reduction I just described is a bit incomplete because Dijkstra's needs to start with a single start vertex and a single stop vertex. This problem doesn't have that because it's just going to be defining the entire first row as the places to start. So one of the questions to think about before class, because we'll talk about it in class today, is how can I actually change this image to make sure it's a graph that Dijkstra's can be run on as is? Because in order to do a reduction, we need to have a graph that we can just run the plain old algorithm on. Now, to kind of wrap things up, we talked about topological sort as being a very applicable way of trying to sort things in a graph, which show up in a lot of applications. And then we talked about kind of this idea of reductions, which is going to be an essential tool in your CS toolbox to solve problems. I promise you, you've already been using the idea of reductions when trying to solve problems. You just didn't have a vocabulary to describe it as such. It is such a powerful tool. And I do want to mention there are so many applications of this that we can not even start to enumerate. So I have a list of just a couple applications of well-known reductions, being able to reduce shortest path in a directed acyclic graph with negative edge weights, reduces to just topological sort. Same thing with two coloring a graph. Coloring graphs is a thing from graph theory where you try to assign each vertex a color such that no two neighboring vertices have the same color. That reduces to this problem called two-sat, which is essentially trying to satisfy some logical formulas. Lots of really clever and non-obvious reductions solve really important real-world problems. Now, not as pressing to the all of humanity and computing, but another example of a reduction would be making sure you stay on top of all the work at the end of the quarter reduces to the task of starting early on project 4 and the remaining exercises. So reductions are things you'll see all the time, even outside of this course, but we wanted to make sure that we had a vocabulary to describe all of these things.